Since this past summer, I've been the architect of Bing Maps, which actually wasn't called Bing Maps over the summer, but that's basically what it is now. It's Microsoft's mapping software, and if you like virtual reality and the real world software as well, Virtual Earth is part of that group too. I'm going to be talking mostly about Photosynth. This is work that began with a project called phototourism, which is a very nice industry academia collaboration that happened about 3 years ago between the University of Washington and Microsoft Research. Noah Snavely was a grad student advised by these two people, by Steve Seitz and Rick Zaleski, one of them at MSR, one at UW, and that was his thesis work. What Noah had done was to take sets of photos from Flickr and reconstruct three-dimensional environments from those photos. So this is one of the data sets that he actually used. It's 500 pictures of Notre Dame Cathedral. And from those photos alone, without any additional information, using his techniques, we were able to take all of those photos and figure out those orange pyramids on the ground are where the photos were actually taken from. And that point cloud, that three-dimensional kind of sketchy reconstruction of Notre Dame, is done also entirely from the photos. So this is this inverse problem called computer vision, and it has a very long history. So this is the sort of thing that gets very different sorts of reactions for people inside the field of computer vision and outside. Outside, it's perceived as being incredible. This is something that most people don't know is possible. But I would argue that we're now really coming into the maturity of that field, and what's incredible now is going to be absolutely commonplace within 5 years. It's an inverse problem, and it's an inverse problem to graphics. And what I mean by that is in the same sense that optical character recognition is the inverse problem to printing characters on the screen, for example, or that speech recognition is the inverse problem to speech synthesis. The inverse problem is always a lot harder than the forward problem. The forward problem is generative, and the inverse problem is ambiguous. So the way the algorithm works for doing this, in brief, is you take a set of photos and extract features from those photos. And what those features look like are points of interest scattered across the places on those photos where there are things happening in the pixels nearby. And then when you have the same feature detected in multiple photos, those are matched. And then those matched features form a kind of a graph or a network. And now you go into the reconstruction phase. And the reconstruction phase is all about assuming that each one of those features that's matched across multiple photos corresponds to the same three-dimensional point in space, x, y, and z. And we have now lots and lots of unknowns. There's x, y, and z for every matched feature, as well as x, y, and z for every camera, because that's not known from the beginning either, and the focal length and the angle. And you just keep on moving the points around and moving the cameras around until what's called the reconstruction error drops close to zero. The reconstruction error being just, well, if I have the x, y, and z for a point, and I'm proposing certain positions and orientations for the cameras, then I know where on the imaging plane those points ought to be observed. And I know where they actually were observed too. So the difference, the lengths of all those line segments correspond to an error. So you just keep moving the points, keep moving the cameras until the errors drop to zero and you're done. So this is how these feature points actually look. This is from a photo of the space shuttle and another set of feature points. And now when you match those two, you get these correspondences. So the basic idea here is that this matching business works to the extent that the description of those feature points is invariant, meaning doesn't change, based on what kind of camera you use, what time of day it was, what angle you took it from. So it should be invariant to all of those things. And yet, at the same time, maximally informative about what it actually was in the world, what feature that was in the world. And those two things are in tension with each other. If you make something that's too invariant, then it can't distinguish different features in the world from each other. On the other hand, if it's too specific, then even a slight change in viewpoint is going to break it. So you have to really balance those two things, and there's some black art in doing that the right way. Now, you take all of those feature points from these photos, you match them by putting them into an index and looking for nearest neighbors. You go to the 3D reconstruction. I think I've already described, at least in as much depth as I can here, how that works. So now I'm going to show you what we did with with this technology in Photosynth, which was first released publicly in August of this past year. We made a website called photosynth.com, and it's a little bit like Flickr or like any of these other sorts of media sites, social media sites in which people can contribute photos and then those can get viewed by others, but with a twist, with a difference. And the difference is that in order to view a synth, originally we required you to download a control that runs in the browser, an ActiveX control. And the reason we did that, in addition to the fact that you need the ActiveX control to view things in 3D, is also because doing all of the math of reconstructing the relationships among all of those photos, that takes a lot of compute. And we actually did this on your own computer as you're uploading the photos. And we're sort of exploiting the fact that, at least outside of Japan, upload of data is extremely slow. And so while it's uploading, it's using your machine to do the computer vision at the same time. So it's a big distributed computation project as well. So a synth, what does a synth actually look like? Well, so there's a synth featured on the front page, of course, and I'll pull up one of my favorite ones. So this is our nanny, Jessie, and it was at the time, I think, a very unusual example of a human subject being synthed. So when you synth and you take photos of something from different angles, Photosynth figures that out, and it's able to figure out that there was an object there, or something of interest that you took from multiple angles, and that's when this halo appears. So when I drag the halo around, I get a sort of sketchy three-dimensional representation of Jessie, and each of those segments corresponds to a photo taken from a different point of view. So I can move around to different points of view. I took some close-up photos of her tattoos, and the other technology that Photosynth incorporates is Seadragon, which was our little startup. And one of the things that Seadragon lets you do is experience multi-resolution content on the web in extreme detail, and maybe more detail than you really want. But this is one of those things. You know, our digital cameras, even ones in phones nowadays, are 5 or 8 megapixels, and that's an extraordinary amount of information. It's much more than you can usually see on a photo sharing site without using something like Seadragon, some sort of multi-resolution imaging technology. Now, one of the premises, one of the things that I think really captured people's imagination about phototourism and photosynth when we first started talking about it in public was this idea of using collective intelligence to map out the world. You know, if we can reconstruct Notre Dame Cathedral by going to Flickr, then is it the case that large parts of the physical world are already there on the web, just waiting to be reconstructed in 3D using the photos that are already available? And this idea got a bunch of us very, very excited. But the results, I would say, are mixed. They're mixed. The results are mixed. This is why. So if we take a famous place like Piazza Navona and we do a regular image search on the web, you get tons of 88,000 hits on Bing images, roughly the same on Google, and of course many of these images are less than a megapixel. They tend to be quite small. If you find images on the web, they often will be reduced to very small size because they're not using Seadragon, and that means that they're not all that useful for reconstructing. But worse than that, the images are all taken from the same places. So you get better images if you go to a website like Flickr. So these are not pictures that are just on the web at large, but explicitly on photo sharing sites. You get fewer images, 29,000 on Flickr, but when you compare with the entire web at 88,000, 29,000 is quite a lot, especially since most of these are really large and beautiful images. And this is just one photo sharing site. So when you add up all of the big photo sharing sites, you get huge numbers and very high quality. However, the connectivity patterns among those photos are the somewhat dismaying part. Well, dismaying, I don't know. It's interesting. So this is an example of a graph of connections between photos of the Ta Prohm temple in Cambodia. So each of those circles represents a photo, and I've drawn here an edge between two photos when they share feature points. In other words, when they're viewing something that's the same in 3D as a neighboring photo. And what you find is that there is, in the case of Top Prom, there is in fact one what's called mega connected component, meaning one set of photos that's all connected and that's fairly large. So both of these big clusters and this stuff over here and these things all connect together. This is actually some images of a particular place in the front of the temple that everybody takes, and another place at the back of the temple that everybody takes. Right, this is exactly what you find. People are not very imaginative, I suppose, and they take the same picture again and again and again and again, and the only thing that changes is which face is in front. This is to the point where there have been some people not so facetiously suggesting cameras that consist of nothing but a GPS and a compass with no lens. That if you go somewhere and you click, it'll just look up whoever took. And I think if you did the small twist where you take whoever your traveling companion was and you insert their photo into the center, then you'd be done. That'd be it. So that's what you get. You get these very, very peaky distributions. If you think about a statistical distribution over space, over X and Y and orientation and so on, over the entire Earth, where are photos taken of what? It's a distribution that has very, very high peaks in a desert, right? Otherwise in a desert of zeros. There are interesting things, of course, that you can get by looking at many, many images of exactly the same thing. Like when there are fig trees in the Angkor Wat temple complex that grow up and then are cut back, and damage that happens to the stones, and you want to see this at every possible time of day, and you use a slider to look at its evolution over time. You can do that sort of thing, but you can't really wander around the Angkor Wat temple complex based on Flickr photos. That doesn't really work out. Now, on the other hand, one of the really nice things about launching a service that's explicitly about people creating synths, and they're starting to really become a very active community of people doing this now, is that people photograph differently when they use this thing. They take photos to synth. On the front page of synths of Notre Dame, of which there were quite a few, even after those first 3 weeks, there was already one synth that was way better than what we could reconstruct from Flickr. And all it took was one person photographing it sort of systematically. So this is one person just taking all kinds of different views and close-ups, and that's the Pointcloud. We like to tell the story always about the wisdom of crowds and how the crowd does better than the individual and so on. But in this case, the individual does a lot better than the crowd. Although a crowd of individuals might do better still. So that's one of the directions that we're taking Photosynth next. People synth all sorts of stuff. Like there's this little community of people synthing fruit and so on. So people synth all kinds of stuff, but especially among the top favorites, a great many synths are geolocatable. So I'm graying out now the ones that are not geolocatable. And by geolocatable, I mean correspond to a particular place on Earth at a reasonable scale, that's not too different from a map, and that are not private environments. They're not somebody's bedroom. If they're indoor spaces, they're public galleries and things like this. So when you look at a breakdown of those top 100 synths, you find some really bizarre stuff that I certainly didn't anticipate. So art is very popular, which is very nice. So 10% of these top 100 synths were of public sculptures and things like this. Lots and lots of archaeological sites. So by now, every famous archaeological site has been synthed, most of them many times. Lots of beaches and coastlines, and this one is especially intriguing. Lots of aerial synths. So people do it by taking photos from small planes, by taking panoramas from very high places, from skyscrapers and overlooking canyons. They do it using cameras attached to kites. It's pretty cool what people are doing. And this is just a typical example of one of these aerial synths. So this is a little resort peninsula in Croatia, in a place where none of the mapping sites, I might add, have particularly good vector data. This is just one person's aerial synth of Primosten from above, which has entire islands that are not even visible in the map. So this is just a view inside that synth. And as this guy flew over the town, he took aerial images that are more detailed and of higher quality than any of the aerial imagery on any of the various mapping sites on the internet now. So I think this is really an interesting idea and trend of having even images from the air, even images of very large parts of the Earth getting crowdsourced like that. All right, so I'm going to show one last thing before stepping down, which is a video of some of our newer techniques for doing reconstruction. So this is just a point cloud now that I'm showing you, and I've just paused it. It's of Kelvin Grove Art Gallery, and these diamonds in the sky over here are the cameras. I think this was done with a helicopter, and what you're seeing down here is just points. Okay, so it's just the Photosynth point cloud augmented with stereo techniques. So that's the level of three-dimensional reconstruction of things on the Earth that one person can do in 10 minutes from a helicopter. And again, this is just the point cloud. Of course, if we really going to the next step in doing complete 3D reconstructions is obviously something that we're very interested in doing as well. And I'm hoping that this is the kind of thing that over the next 5 years is going to really take a lot of our physical experience of the world visually and create an online version of it, a mirror world version of it. And of course, that gives you all sorts of interesting superpowers, right? It lets you teleport yourself anywhere in the world you want. It lets you experience augmented reality by giving you a model against which your camera can match its visual experience, so that semantic information can be added on top. Really, all of this is about extending our abilities and extending our senses, extending our perception and our understanding of the physical world around us. I'll end there. Thank you very, very much.